got made. Do you want to start with then some questions from homeworks before we continue to pick away at what we've been working at?
Could you do 27?
From
5.2.
5.2? Sure hope so. So this says to prove that the integral from a to b of x dx is b squared minus a squared all over 2. So we'll start with our definition of an integral. So my delta x is going to be b minus a over n, right? And my xi is going to be a plus b minus a over n times I. So just the starting point plus the change in x. And then that change of x has to be multiplied by I, because each time you want to go one more interval over, right? So for proving this, we'll say this is equal to the limit as n goes to infinity of the sum, I equals 1 to n, of we'll write it this way first, f of xi times delta x, right? And our f of x in this case is just x, so I'll just erase off that for me. Hi, Addie. Thanks, dude. Hello.
Hi.
Thanks. Hello, this is for you. Okay. So next up, let's see, what do I want to do with this? So this piece doesn't depend on I anymore. So let's kind of pull that out front of the sum. And I'm going to distribute that sum across the a and the b minus a over n times I. Violet, are you still okay?
Yeah.
Okay. So the sum of a constant, if I add up n of those a's, I get just n times a, right? And here, for the second sum, I can just, that part doesn't depend on I, so I can pull that to the front. Go ahead and do some more rewriting. And the sum of I is, from 1 to n, is n times n plus 1 over 2. That was one of those identities that was given to us in the textbook in that section. So now it's just going to be like an exercise in cleanup here a little bit. So those guys are going to cancel out. And let's see where we're at here. So we have n plus a time, or plus b minus a times n plus 1 over 2, right?
Is it a plus or a times?
Oh, sorry. Yeah. Thank you. So if I, right here, I'm adding up n a's. So if I do that, I get n times a, right? I get n copies of that a. Does that feel okay?
Yeah.
All right. I guess let's FOIL and kind of see. And I'm
just kind of like
know the identities. What do you mean?
know
So like this, that was an identity that was given to you in your textbook.
I just don't know how you get all these random letters.
Yeah, that was, again, that's a formula in the textbook. In the section, it lists that in the notes. I have that highlighted. That's what I'm using there. If you did sequences in series in Algebra 2 like we used to, that's the sum of an arithmetic sequence formula. Yeah. But that's where we're at. So just FOIL that out, and actually I'm going to do that and make a common denominator. So when I add that in, I end up with NB plus NA plus B minus A all over 2. So far, so good. And I'm going to now multiply those two fractions together. So the denominator is easy. That's just 2n, right? But then I have to do like a fancy FOIL here. So that's going to give me nb squared plus NAB plus b squared minus AB, and then minus NAB, so those will cancel, minus NA squared, and then I have minus AB plus A squared. And the last thing I'm going to do is I'm just going to write this numerator kind of in a factored form. So I'm going to factor out an n from the terms that I have in n. So I have n times b squared minus a squared. And then I have minus 2ab plus b squared plus a squared all over 2n. The limit I'm trying to do now is an infinite limit. I have a rational function, a polynomial over another polynomial. The degree of the polynomial on top is 1. The degree of the polynomial on bottom is 1. So the limit is just going to be the leading coefficient of the numerator over the leading coefficient of the denominator. And that's what we're trying to get to. Woof. Again, would I ask you to do this? No. Will the AP ask you to do this? No. Okay. Is it good to be able to do? Yeah, right? Like, and at least being able to follow what I'm doing. Like, okay, all right, okay, a lot of algebra. There it is. All right, I believe you now. Now, I want to point out that using the fundamental theorem of calculus, the antiderivative of x is x squared over 2. And if I evaluate that using the fundamental theorem of calculus, boom, it's right there. It's like one line. That's a nice tool, that fundamental theorem of calculus. So again, pointing out to you that the power of that theorem that allows us to just get rid of all the summations and the limits and like, go away. We don't need you. Which is pretty doggone cool. Others, questions from homeworks? Happy to do more. And then we'll kind of finish up 5-3 and just pause here and do a little bit of practice after that. Paulo? Mm-hmm. Okay. It was one of the homework quiz questions? Yeah. Okay, let's see. That'll take me a minute to find.
I think I remember it.
You think you remember it? Well, you can just tell me and we can do it, whatever you tell me.
Square root 1 minus plus x cubed. Plus x.
Okay. That, and we're asked to do what with it?
Which of the following antiderivative?
Okay. So what I know is that, like, I think there might have been more to it than this. Let me just look it up real quick. It's one of those things like the context matters. You know what I mean? Because the way that's currently written, I don't think that's something that I would have asked you to do. Was this the review questions, or was this
It was the third.
was the most recent problem set?
Yes.
Okay. Or most recent one. Oops. So this should have been on 5-2. Okay. Yeah. Let me just do this. So this is the question, right?
Yeah.
Okay. So we know that this is basically just asking us to do the fundamental theorem of calculus. So the fundamental theorem of calculus, part 1, let's just go back and toss that in here real quick so I can show you why it's that. Let me just grab it. So it says if f is a continuous function on AB, then g is defined by g of x equals this integral is continuous and differentiable, and the derivative of g is f. So it tells us then that g is an antiderivative of f, right? If I know that. So that's what I would be doing. I would just be writing, okay, so that'd be like my antiderivative for f. That's it. So it's just kind of using the fundamental theorem of calculus part 1, because it's that theorem is literally saying that if I write this integral function g, that it is the antiderivative of f. Right? If the derivative of g is f, then g is the antiderivative of f, right? So that's it. We would have just picked option E. Does that satisfy you?
Yeah, I just didn't know the theorem.
Yeah, that's okay. Again, it's getting part of getting comfortable with it, right? I want to point out for the homework quizzes too that like we'll do most of these this semester on the MyEP. I'll include. Portion of it will be stuff we've been doing recently, and a portion of it will be review stuff, whether it's a multiple choice or free response or whatever. So I'm going to give, like, if you get max score, I'll give you 11 out of 10. Miss 1 point is 10 out of 10, and then so on down. So I know they're timed. I know that's like right and wrong is kind of stressful, but part of it is building in that you can recover points that you missed by later on just by getting 11s instead of 10s or whatever. If it's, oh, I didn't do well there, it's okay, right? And then some are dropped anyway. So, like, does that make sense? Okay, feel fair?
So is each question worth 1 point?
Yeah, basically 100% is 11 out of 10, and then you lose. For every question you miss is 1 point less. So it's not like each question, because it's out of 10, right? So if you get nothing right, you still get a 6. So it's not a 0 if you do it. You know what I'm saying? Again, the rationale being there, I want to like put a timer on you guys and get you used to having to do these things kind of quickly. Have to think about, like, what have we done before and how does that connect to what we're doing now, especially in the free response questions. They like to take disparate ideas and kind of package them together inside the same problem. So I hope that feels like not an unfair homework quizzing format. Okay, let's finish up section 5.3, and then I have some like practice stuff we're going to use or do today, just working on like this concept in the fundamental theorem of calculus part 1. Okay, so I know that that's still kind of new and doesn't feel real comfortable yet. So I have some extra practice. And just practice. We're just going to do them in class. All right. So we left off here. It says find the area under the parabola y equals x squared from 0 to 1. So that area I can find by just doing the integral of x squared from 0 to 1. The fundamental theorem of calculus part 2 says to do this, I can just take the antiderivative of x squared. What's the antiderivative of x squared? X cubed over 3. And then if I evaluate that from 0 to 1, I'm going to have 1 cubed over 3 minus 0 cubed over 3. So I just get 1/3. Feel okay? I want to point out too as well, if you have your graphing calculator with you, you can take it out and follow along. But all of these definite integrals can be done on your calculator. So a definite integral is where you have numbers in the bounds of your integral. So to do this problem, I'm going to start by pressing the math button. And I'm going to scroll down to, on my calculator, it's command 9 that says FNInt. That stands for function integration. So I'll press enter there. And now I'm just going to type into my calculator exactly like what it looks like on my sheet of paper. So 0 to 1, x squared, and then dx. And press enter. Bam. Yes, Alex. Sure. That feel okay to you guys? All right. Let's continue on. Let's do some more examples. So here it says evaluate the integral from 3 to 6 of dx over x. Again, when I look at this, I'm going to think about it this way, where it's a little bit easier to see what I'm integrating if I separate the dx off to the end like that. Again, we'll use the fundamental theorem of calculus part 2 here. What is the antiderivative of 1 over x? What did I take the derivative of to get 1 over x? Natural log. Very good. So that'll just be the natural log of 6 minus the natural log of 3. Now, if there's a multiple choice question on the AP exam and in the no calculator section, that is not how they'll write the answer. They're going to use their properties of logarithms. If I have the difference of two logarithms, remember that's the quotient inside the logarithm. So they'd write the answer as natural log 2. Almost assuredly, if this was like a multiple choice question on the no calculator portion of an AP exam, they're not going to write it as the difference of two logs there. They'll probably, almost assuredly, try to confuse you and use their properties of logarithms to trick you. Don't be fooled by that, though. Remember those. We spent a lot of time in Algebra 2. And probably AP pre-calc. Do you do logarithms again there, right? Yeah. Okay. All right. Next one says find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. So 0 to b, cosine x dx. What is the antiderivative for cosine? Well, the derivative of cosine is negative sine. But what do I take the derivative of to get cosine? Sine. There you go. So that's going to be sine of b minus sine of 0. What is sine of 0? 0. Again, hopefully you can do that without a calculator and without a unit circle. The AP would expect you to be able to do like at least certainly the quadrantal values like sine is 0, cosine is 0, tan is 0, sine of pi, tan of pi, be able to do the quadrantals for sure. So I just get sine b. And then if we wanted to say, find the area when like b is pi over 2, that'll just end up being sine of pi over 2, which is like, yeah, very good. So that's just me doing a for example. Since it was a b on that interval, I can pick any values of b then and just plug them into sine, and that'll give me the area under cosine. Why'd I pick pi over 2 here to stop? What happens to the cosine function after pi over 2? It goes under the x-axis. So now you're going to be accumulating negative areas, and you're not going to be able to do, it's not going to work out quite as nice. Okay. So here's, again, the fundamental theorem of calculus, parts 1 and 2, located in one spot. I wanted to go back here, though, and grab a couple, or take a minute and go through a couple of these properties from section 5.2 that, again, depending on how thoroughly you went through there, you might have missed if you just kind of skimmed through. So these are all properties of integrals. These are things that you should have memorized, things in how you can manipulate an integral. They'll be key to being able to do problems. In particular, on the multiple choice, almost assuredly there's going to be problems that are basically just testing whether you know these things or not, where that's going to be the key to doing them. So the first property here says that if I flip the bounds, so if I go from the integral a to b, or from b to a, and I switch it to a to b, I just pick up a negative sign out front of my integral. Everybody's okay with that? If I integrate from a to a, that integral is 0. Again, because it's a straight line that you're talking about and it has no area. And then we have some properties on like things you can do with your integrals algebraically. So if I have like a constant and I'm integrating that, all I have is a rectangle, right? If y equals c is my function, I just have like some rectangle from a to b. So it's just an area problem. Everybody's okay with that? The next one says that if I have the integral of a sum of two functions, I can just distribute that integral across the sum. Likewise for subtraction, right? And the third one says if I have a constant inside my integral, I can pull that out front of my integral and just integrate the remaining function, then multiply it by the c after I do the integral. So those are all things you can do. And then the last property says that if I have an integral from a to b, where c is some spot in between that, I can break my integral up from the stuff from a to c, and then I can add it to the stuff from b to, or c to b, and still get the same thing as if I integrated just from a to b. Which hopefully that makes sense intuitively. Like when we draw the picture, it's like, oh, of course those areas are going to add up to be the same thing. And you can use it in either direction. You can use it to combine two integrals into one integral, or you can use it to take one integral and break it up into two pieces. Most often it's going to be breaking it into two pieces that is going to be how you would use that. And I'm going to show you a couple of examples here in a moment as to like why I would want to do that. So far, so good? Okay. So I wrote up a couple of quick examples to illustrate some of these things that can happen. So let's look at example A here for a moment. This is the integral from 0 to 3 of x minus 2 over x minus 2 dx. Who just wants to write that as 1? What's the problem with that, though? If I draw the graph of this, now let's say this is 1, 2, and 3. I have a hole. Does that matter? How much area am I missing from that hole? I'd be just missing that, right? How much area does that line have? 0. Does the hole matter? No. Okay? So if I'm taking the integral and I have a hole, doesn't matter, doesn't affect it. I can just pretend it's not there. As long as you have finitely many holes, you can ignore them. If you have infinitely many, that's a real analysis situation. That's something well beyond the scope of this class. Can you imagine a function that has infinitely many holes in it? I think we saw one in first semester, right? The textbook cooked one up where they said, f of x is like 1 if, x is a rational number, and then it's like undefined if x is irrational. That's something that on any interval you'd have infinitely many holes. That you can't integrate with what we're doing. But that's not a problem anyone's going to ask you to integrate until you get to like a real analysis course, where unless you're a math major, you're not going to do that. Just being real. Okay, so this is really just going to be 1 times 3 then, right? I just need that rectangle. That feel okay to everybody? What if we ask you to do the integral from -3 to 4 of the absolute value of x minus 2? What's the catch here? What's going to be the problem with that? Do we know an antiderivative for the absolute value? Sure, but it's still going to be integrable. And it's only not differentiable at the corner, right? Everywhere else on the function it would be. What should we do here? What I would do, or what you should do, is we should write the absolute value of x minus 2 as a piecewise function. So the absolute value of x minus 2 is just equal to x minus 2, provided x is greater than or equal to 2, right? Because any values bigger than or equal to 2 are going to give you a non-negative for x minus 2, right? Okay, so if x is less than 2, what do we do? We have to make it negative, right? If x is 0, I get 0 minus 2, that's negative 2. And then if I make that negative, that's doing what the absolute value is doing, right? Does this feel okay? Now, what I'm going to do is I'm going to separate this into two separate integrals. And now, can I do the antiderivative of negative x minus 2 and regular x minus 2? You betcha! In fact, those are easy antiderivatives to do. I'm really excited about that. So the antiderivative of x is x squared over 2. And the antiderivative of 2 is 2x. And I distributed the negative sign through there. Is that okay with everybody? And then similarly here I have x squared over 2 minus 2x from negative 2 to 4. And then I can just kind of continue on, right? Alternatively, the other way you could have thought about this is you could have said, oh, well, I know what the graph of the absolute value of x minus 2 looks like. It's basically a V. So if I just take like negative 2 and make a triangle, and then out to 4 and make a triangle, I can do it that way as well, right? So at negative 2, the height is 4, and the base would have been 4. And then over here at positive 4, the height would be 2, and the base of the triangle, we've gone 2 over. Right? So you could do it that way as well. That's maybe easier, but it required you to know what the graph was looking like. And the function to be an absolute value of a linear. If it's like the absolute value of a quadratic, you're out of luck trying to do that graphically, right? Now you have to write it as a piecewise and then break the integral into chunks. Is this okay? And then the last one I wanted to show you guys was just like if I'm integrating a piecewise function, we're going to do the same trick we did for the absolute value. This is actually maybe even a little easier because the chunking is already done for me, right? My first integral should go from negative 2 to what value? 1. And that should be the function 2x plus 4. And then we'll go from 1 to 4 e to the x dx. And then it's pretty straightforward from there, right? Antiderivative of 2x is x squared plus 4x. And then the antiderivative of e to the x is just e to the x. And we plug some stuff in and blah, 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 blah. Does that feel okay? Again, I want to do some more like sneakier integrals than what was listed in the examples. These are things that like you have all the tools to do, but maybe aren't like how to do this is not entirely obvious. And I wanted to connect some of those ideas that we saw in 5.2, some of those integral properties, into actually doing integration using the fundamental theorem of calculus rather than like with these awful limit of sums, which we will never do again. Okay. I have for you guys some practice stuff. These are just like AP style questions of using the fundamental theorem of calculus. Just help us practice on this. I have, remember, it's 6 or 7 questions here. They're all the free response styles. This is one that just like, we'll do some of this stuff together, and then we'll go do the first one together, and then from there on, I'll let you guys work on stuff and ask questions and all that jazz. I'll post some answer key here. Later, I have the answer key done. I just don't want to post it until you've had a chance to like ride the struggle bus a little bit, kind of getting up to speed. That's what I want. All right. So let's have everyone look at number 1. So we're given a graph of some function f. It says the graph of the function f shown above consists of 2 line segments. Let g be given by the function g of x equals the integral from 0 to x of f of t dt. When you see that statement where you have a function defined as an integral where the variable is one of the bounds of our integral, that is a fundamental theorem of calculus problem. Whenever you see that, that's what you should be thinking. It says then to find g of -1, g prime of -1, and g double prime of -1. So let's start with the first one. So g of 1 will be the integral from 0 to -1 of f of t dt. So far, so good. Now, do I know the function formula for f of t? No. So am I going to look for an antiderivative? No. How am I going to calculate this integral? I'm going to look at the area under the curve. Now, the first thing I'm going to observe here is that the bounds of my integral go from big to small. You guys see that? So the first thing I'm going to do is make that integral negative so that I can switch my bounds. Is everybody okay with that? And now I'm going to look for the area from -1 to 0. Which is just that triangle, right? So the area formula for a triangle is 1/2 base times height. The base is 1 and the height is 3. So that should be -3/2. Yes, Michael?
Why does it matter when you switch the bounds?
Well, if you're looking at the area from 0 to -1, you're going this way. You have to remember that everything is going to be negative because you're going in the opposite direction. Because your change in x is now negative. So I always just like want to go from low to high so I don't have to remember that. I'm just going to use the property.
So I won't make it negative and I'll put the
Correct. Yeah. Does that feel okay with everybody? Okay. So g prime then of -1, well, let's start with just g prime of x. That's going to be the derivative of the integral from 0 to x of f of t dt. What does the fundamental theorem of calculus part 1 tell me about the derivative of an integral? They cancel each other out, and I'm left with just f of x, right? Is everybody okay there? That when I do that, the variable in the bound becomes the variable in my function. Now, technically, I also have like times the derivative of that bound. There's really a chain rule thing going on there, but since it's just an x, the derivative of x is 1, so it doesn't really matter. But if that was like an x squared up there, you make a big big ding dong difference. Okay. So g prime of -1 then is just going to be f of -1. So if I go back to my graph, f of -1 is just 0. If I'm looking at the second derivative, I know the second derivative is going to be the derivative of g prime. I know the g prime was just f of x. So the derivative of f of x is, just call it f prime of x. So the second derivative of g at -1 is just going to be the first derivative of f at -1. Is everybody okay with what we did there? Tell me to stop and slow down if I'm going too fast on anything. Okay? Just trying to walk through doing this stuff together and get us used to thinking about this. There's a bunch of practice in here, so you have lots of chances to try it on your own also. Now, how do I do the first derivative of f if I don't know the function for f? All I have is this graph. It's the slope, yeah. So it's just going to be the slope from this side, right, where -1 lives. So it's going to be the slope from -2 or -2, -3 to 0, 0, 3. Did I do that wrong? Oh, of course I did that wrong. Look at how stupid I am. 3 minus 3 is 6. Or 3 minus a -3 is 6. That should just be regular 3. Oopsie-daisy. That feel okay? All right. Part B says, for what value in the open interval -2 to 2 is g increasing? Explain your reasoning. So if I'm looking for where a function is increasing, what do I need to look at? I need to find where its first derivative is positive, right? Remember that the derivative of g was f of x. So we're just looking for where f of x is positive. So I'll go to my graph. Where is f of x positive? -1 to 1, right? Just to where it's above the x-axis. Yeah, I think that right there, I think is plenty of reasoning, right? We showed why the derivative of g is f of x in the previous problem. So that work still counts. We don't have to redo that. And we just showed that g is increasing implies the first derivative is positive, which was just the f is positive, and we don't have to explain from the graph, right? Like that's self-evident, but that's enough of an explanation. Does everybody feel okay? Part C says, for what values of x in the open interval from -2 to 2 is the graph of g concave down? What do I need to look at to tell if a graph is concave up or concave down? Second derivative. Should it be positive or negative if I'm concave down? Negative. Very good. Which is the same as where f prime is negative, which is going to be where f has, or where f is decreasing, right? So if I go and I look at my graph, where is f decreasing? From 0 to 2. Does that feel okay there? What I'm hoping we see in doing this is that, like, if you know what to look for and what you're doing, most of these questions are pretty conceptual. There's not much to show or do. I'm kind of explaining my reasoning as I go along, but mostly I'm doing that symbolically. I'm not going to use words, right? Ideally. Part D says, on the axis provided, sketch the graph of g on the closed interval from -2 to 2. Okay. Okay. So what I know from looking at this is that I know that g is increasing here from -1 to 1, that we're concave down here, and using the same reasonings as from before, if we're not increasing, then we have to be decreasing. And if we're not concave down, we have to be concave up, right? And so I know the shape of it then is going to be like, have some idea for the shape. I think to get the rest of this, I'm going to just evaluate some points for g now that I know how the thing is going to bend. So let's do -2, -1, 0, 1, and 2. And here's the thing. -1, we already did that, right? That was 3 over 2. Oh, sorry, -3 over 2. Thank you. So if I go out to 2, oh, gosh darn it. If I go out to 2, then I'd be also including that triangle along with that triangle, right? Everybody see that? What are the areas for those going to do? Cancel out, So guess what g of negative 2 is going to be? Just going to be 0, right? Everybody feel okay there? What's g of 0 going to be? Also 0, right? The integral from 0 to 0 should be 0. If I do g of 1, that's just going to be that triangle with a positive area, right? Because we're going forward. So that should be 3 over 2. And if I go all the way out to 2, I'd have this triangle and also that triangle, which cancel out. So that should be 0. So that should be my graph of g of x, should look something like that. Notice that it's decreasing in the right spots, right? We're decreasing on both those spots. That we're increasing in the right spot, yup. We're concave up in the right spot, and then concave down in the right spot. Okay. In particular, notice that when I found these points for G, I didn't really care what the number was so much, right? Just looking at, okay, this area and this area just cancel out, that gives me a 0. This area and this area cancel out, give me a 0. In general, I want to do that to save myself time as much as possible. If I want to look at the thing and just be like, okay, like those spots is the same as those spots, like that just cancels out or it accumulates more or less or whatever. Sound okay? All right. I'm going to stop here. I'm going to let you guys work on the remainder of this kind of packet. Take the next 20 minutes or so. Get a start. Start on number 2. Feel free to converse amongst yourselves. Talk to your neighbors. Find a partner that you work well with if you want. That's fine. This packet isn't homework. You don't have to turn it in. You do it or you don't. Do what you feel. My recommendation is you should do this. I think it's valuable. I wouldn't have picked these things out and given them to you if I didn't think that this was an exercise worth doing. Next class, we can ask some more targeted questions about stuff from this. And I'll post an answer key for it also. Yes, Michael. Well, you should do the 5.3 homework from this, right? That's the 5.3 homework. The packet is just extra practice. I don't think we need to make it part of the problem set, right? Like we're going to do it anyway. You know, I don't think you need to stress on it. It's for practice. I will post them next class, yeah. I want you to have like a couple of days to try, you know, and ride the struggle bus a little bit and see what you can figure out. And we'll answer as many questions as you guys have next class. And I have the answers posted, and whatever you couldn't figure out, you can look at. And I have like my worked out solutions where I give you like maybe more than when I post the free response question answers from the MyAP, which sometimes leave a little bit to like unpack on what they're saying. So most of these, or all of these problems that I just assigned you, I did and I wrote out much in the same way that we just wrote out the work for this problem, where I give you what I'm doing to do it, which is probably helpful or more helpful than just like the MyAP. Like, here's the answer. It's like, great. But how did we get this? Oh, I get 1 point for saying this. Great. I didn't. What? How, why? What? How did I get from this to that? Kind of thing. You know what I mean? So just kind of looking ahead. You know, I have 2 more sections in chapter 5 to kind of do before we're looking at test time. The majority of your test points are going to come from like just being able to do integrals. So like if it's piecewise, can you do the integral? If it's not, if it's, you know, definite or indefinite, we haven't talked about what indefinite means, but it's basically just doing the antiderivative and not plugging any numbers in. And then we'll talk about the U substitution here in section 5.5. That's another integration technique for problems that would have required a chain rule derivative. To undo a chain rule, we're going to use something called U substitution. We'll show you how that works in 5.5. But majority of your points from the test will come from like being able to do integrals where you have to do it, you know, a U sub, where you have to do a definite integral or an indefinite integral, or use the graph, or break up an absolute value into a piecewise function and then integrate it, or, you know. This is a very, like, you know, like test 2 was like a lot of just like take the derivative of this thing. This is the equivalent test for integrals. Like just do the, you know, do this integral, do this integral, do this integral. You know, there'll be a little bit of conceptual stuff in there, but the majority of it is like, can you do, you know, like, can you do these integrals? And obviously that's not coming this week, probably wouldn't come next week, because we only meet twice, right? So it'd be like the week after next would be looking at that first test, giving you a time frame, just sitting here talking while you guys are kind of playing around with these new problems I just gave you. Figure I can use this time at least to like communicate out some of our stuff. Everybody's, I think, caught on that I'm using the same OneNote as first semester. I made the teams to do a new notebook. I'm like, why am I doing a new notebook? I'm only in one section. Everybody's already in it. Like, so I just changed the name of it or whatever. Yes.
What's the like the system? Are we going to like dropping homework? Like, how's that going?
Same thing. Just drop them into the homework tab in your.
Like if you don't do it. Like,
oh.
Like how many are there?
Oh, it was this. It's the whatever was the. I did the same thing as I did first semester. I think. I don't remember how many did I drop first semester. Two. I don't remember. I'll do whatever I did first semester.
I think it was 2.
Was it 2? Okay. Let's do that then again.
So my tablet broke, like, give me a moment.
Okay.
And I submitted a work on my phone, but like it doesn't show up. It's like
Let's
when
look
you
at.
checked it in, it just didn't show up.
Okay, let's take a look here on my end. I'm gonna stop the recording.